I'll go ahead and get started. I'm going to tip my light a little bit too. Hello, I'm Rebecca Thorndike-Breeze. I'm here with Michael Trice, Jesse Stickled-Sarah, and in spirit, Andreas Karatsalis, and we are coming at you, most of us from Massachusetts. Andreas is in Greece, but for those of us in Massachusetts, it's 7:32 p.m., so it's a little dark in our rooms. Welcome, we're very happy to have you here. I'm going to keep my introduction as brief as I possibly can. So we are presenting our work that we have done in our program to bring our programmatic approach, which Michael will discuss in his video, to an aerospace engineering program that had, well, I will let the presenters speak for themselves, but we'll be showing a video from each of us, and then we will have a short time for Q&A, hopefully about 10 minutes at the end. And since it's kind of truncated, I also wanted to include a handful of sort of reflection questions. I'm going to paste those in that right now. These are, I'm not expecting, we don't want you to necessarily answer these questions in the chat, but these are just sort of food for thought to keep in mind as you watch the videos. These are also in the chat on our Whova page, and any questions that you have that you aren't able to ask during the Q&A, please post them on our Whova page and we will answer them there. So without any further ado, I will let Caleb go ahead and get the video started with Michael Trice's presentation.
Hello, my name is Michael. I am a lecturer at MIT, and I'm going to be the first speaker on this panel, and I'm going to talk broadly about how we apply reasoning and stasis in writing in the disciplines, particularly how we work to make disciplinary knowledge that is implicit more explicit for our students. So I wanted to start with Mindorf and Pace's decoding the disciplines figure. Figures and visualizations have become very important to us as a department. I'll talk a little bit about that towards the end of the talk, but I think that this figure does a really nice job of outlaying the core issue of what the process looks like in the WIT environment. So they start with a very useful question of what is a bottleneck to learning in this class? And that's a great question for us because we don't teach in standalone communication or writing courses. We work embedded within courses that exist within astro, mechanical engineering, computer science. So I might teach in a capstone course in mechanical engineering, or I might teach in a PhD seminar course in astro about thesis presentations. And so there's always going to be disciplinary faculty that are involved in these courses, often the lead of these courses, and we are going to be there to be able to provide support and instruction on the rhetorical and communicative side of that class. So frequently there's a lot of bottlenecks that we're there to address that sort of arise between how do we work to make the implicit disciplinary knowledge of the faculty something more explicit and available to the students, particularly when it comes to replicating genres. And that's great for leading into that second part of the question, which how do experts do these things? Well, we have those faculty experts, and actually those faculty experts are extremely important to us. We have a process for interviewing and really taking advantage of their knowledge to be able to understand, how is it that they think about creating particular genres? How is it that they think about dealing with various audiences, whether that is peers, others in industry, funders? We want to be able to get a good understanding of how they speak and how they perform particular genres for those audiences, so that we can then move on to this third step of beginning to think about how we model the process that they use in order to be able to make that more available and more visible to the students. And that brings us into that fourth step of how will students practice these, beginning to get into sort of the pedagogical aspect of what sort of activities we're going to design. And I'm not going to talk a lot about steps 5 and 6 within this talk, because that assessment aspect is not something we're going to dive into a great deal in these talks. If you were at the workshop on Monday, you saw a little bit of some of the assessment that we have done in regards to some of the visuals and other teaching tools that we have used, but that's not going to be a focus necessarily here. And then number 7, of course, is what we are all doing here at this conference, which is sharing this knowledge more broadly within our own discipline. So with Beaufort is a touchstone for us, as I'm sure is a touchstone for many of us here within this group. We work directly in discourse communities. We work specifically, as I said, within the Aero-Astro or within computer systems. They're directly with the faculty for those programs, and it's very useful for us in that case to be able to use this kind of framing and being able to isolate for students, writing process versus subject matter knowledge versus rhetorical knowledge versus genre knowledge, because the faculty can provide that subject matter knowledge, and they can provide insights into a lot of these other areas, actually all of these other areas, as I'll get into a little bit of detail here soon. But they can talk through what their writing process is. They absolutely know the genres that they work with and the activity systems that they work with within their field, and most of the time they have an implicit understanding of the rhetorical aspects within their field. And sometimes you get lucky in a field like Aero Astro, and rhetorical knowledge has actually been captured and crystallized a little bit in the recent history of the field. Of course, with Aero Astro, most of the history is relatively recent. Certainly by comparison to the history of rhetoric. But this is a fantastic way for us to be able to work with students and with faculty in being able to demonstrate how all these spheres come together. And one of the core ways that we do this is we use a sort of neoclassical, more of a Fanstock inspired stasis approach to teaching. So not quite true Aristotelian, but more updated and focused on the STEM approach. So these are slide examples of what we might directly show to students through our instruction. Just getting them to understand 5 core stases: fact, definition, causation, value, and action. Understanding that these stases can be opened or closed, and it matters. That's how you perform research, is by opening one of the a point of stasis and being able to engage with it and push it in certain ways, which is kind of a more sophisticated way we find frequently than just what is the technical gap, but figuring out which of the stases you're going to be opening and why you're opening it and in what way you're opening it. And once you've opened a stasis, of course, you have to find a way to begin to close it. Otherwise, you can't make the full argument. And sometimes you don't want to make the full argument. Sometimes you're going to stop at causation and you're not going to move to value and on to action or some sort of policy recommendation. But we want students to be able to understand that they can only go so far with a point of stasis open. So we do use it as a constructive and building model, which is a little bit different than just using it as an invention tool. And I think that both historically and even in a lot of current writing, there's a tendency to view stasis as an invention tool. And we really do view it more as a way of both being able to construct in that video process, but also as a reading tool, as a way to be able to understand and comprehend how genres function, where stases are open in particular genres and why. And thus it becomes something of an arrangement tool for us. And I think that arrangement aspect is extraordinarily important and vital to how we apply stases, both in framing our own pedagogy, but also in how we instruct students. So one of the things we also do for students is we want them to be able to ask multiple questions around each of the stases. So we'll provide them a breakdown of some understanding of what can happen under fact, definition, causation, value, and action. And one of the reasons that this is useful is it allows them to engage in different parts of a genre with these stases. So how does this happen versus why did this occur under causation? It gives an opportunity to see how causation can vary from one genre to another, or how causation appears differently within a particular genre, and sometimes differently in a particular field. For example, the nature of definition is not going to be the same in computer science as it is in aero-astro or mechanical engineering. Definition can plays a different function in computer science because it's more central in defining the core concepts of how a system functions, as opposed to a where those classes where that sort of hierarchy and class structure may be less rigid and expansive in other fields. So the big takeaway there is really just that the stases do operate and ask different questions in different disciplines as it does within different genres. And we want students to have a broad grasp of what that means and how to be able to apply that as we move them into being able to sort of, code various stases within genres in order to see where does an introduction, is it going to deal primarily in fact, somewhat, but it's probably going to be mostly motivational. And then, where are the causative elements going to occur? For some papers, there's going to be a lot of causative elements that occur in the methods. For others, it's going to be more in the results. And we want them to be able to sort of be able to map and see how this is occurring in a paper so that they can use that for arrangement purposes. One of the great things that we have had a lot of fortune with in Aero Astro is that the faculty have embraced this understanding of stasis. This is actually a revised version of the chart that a faculty member in Aero Astro created. And in this version, for the particular genre of presentation that they're talking about, they wanted to see fact and then definition, and a technical gap. We see some Swellsian terminology coming in here, a solution, and then an evaluation. And this is how they saw the presentation that they wanted working, which is great. It's a rearrangement. We've got some new terminology here, and the questions are really where things come to life. Under fact, we see domain setting, problem identification, why should we care? So we begin to see some much more disciplinary terminology coming into here. Domain setting, problem identification. Under definition, we see formal problem statement or hypothesis. What are the parameters? What are the constraints and variables? We see more and more disciplinary language come in, and this is sort of an ideal situation for us. This is where we have engaged with some rhetorical concepts and skills within a class. We've spoken with faculty, and they have come back with their understanding of this rhetorical approach, but put into a disciplinary context with disciplinary language. And we can do a lot with this. This may not perfectly align with how we view the stases, but it gives us a ton of insight into the construction of a genre and how disciplinary language and core concepts begin to work within these genres, which is something then, of course, that we can make more explicit to students. So we talked a little bit about swells there in that previous slide, but one of the things that we do look for when it comes to rhetorical moves is the application of professional examples, the application of student examples. We want students to be able to see both those professional genre examples as well as their own student examples, and then historical representations. We're very interested in being able to capture some of those, and Aero Astro is great in having things like NASA's design review process. So that concept design review process, preliminary design review process, critical design review process. That's a great method of being able to establish what genres are and what particular rhetorical moves are within those genres. And then there's something like the Hellmeyer Catechism. So this is the Hellmeyer Catechism. What are you trying to do? Articulate your objectives using absolutely no jargon. How is it done today? What are the limits of the current practice? What is new in your approach and why do you think it will be successful? Who cares? If you are successful, what difference will it make? What are the risks? How much will it cost? How long will it take? What are the midterm and final exams to check for success? And you can sort of see that design review process beginning to evolve there at DARPA in those final questions, actually. But this is great. This is outlining rhetorical moves. There are historical representations within the field from a trusted institution that is essentially giving us a list of the core rhetorical moves. They probably don't apply to every genre. A really nice activity is to ask students, okay, you've read a genre example. What are the rhetorical moves from the catechism that you see in this particular genre example? Why does it have some and not others? How does that apply to the audience? This is a great, useful way of being able to, when you don't have a lot of access to an expert, to be able to jump straight into some of this disciplinary analysis. But it also is a very useful tool for taking something that Aero-Astro faculty know really well and saying, well, these are just rhetorical moves. And not only are they just rhetorical moves, this question here, this is a question of causation and this is a question of fact. So they're actually implementing the stasis here, and that creates a lot of buy-in when you can communicate with them about that rhetorical moves and that stasis play a critical role in how they reason about their field already and how that can help students. Then we gain an enormous amount of trust in that process. All right, so that is a very fast overview of our approach to WID at MIT, and I'm going to turn it over to my fellow panelists to dig into some more details. Thank you very much.
So now, yes, Caleb is transitioning to the next video.
Welcome to the second presentation for our panel. My name is Andres Carazzales. I'm the Associate Director of the program in Writing, Rhetoric, and Professional Communication at the Massachusetts Institute of Technology. And today I want to talk to you about habituation and how to teach communication in a disciplinary program, specifically Aero-Astro, or as we call it at MIT Core 16. Let me start by giving you a little bit of background, some context about what the program is and what our program, RAP, is all about. As you can see, Aero-Astro is a field dealing with rockets, airplanes, and autonomous systems, mostly related to aerospace and engineering, but it captures undergraduate degree students from anywhere like material science engineering all the way to robotics, and very often all the way to mathematics. So it has a very interdisciplinary approach, and a lot of their capstone courses are very well received by MIT students from all departments. Now a little bit about our program, RAP, Writing, Rhetoric, and Professional Communication. As you can see in this little excerpt from our website, we work with about 4,000 students a year in about 100 communication intensive subjects. This means that we are embedded in courses both in the humanities, as we call them CIHs, communication intensive courses in the humanities, arts and sciences, and in CIMs, communication intensive courses in the major. We have about 40 lecturers who teach in all these classes, some of which are semester long, others are workshops, but for the most part, they are embedded in classes that have a different disciplinary focus other than writing and rhetoric. Now, within that context, we have managed to place ourselves at a point, and I'm going to take you all the way to the end, let's say here, so that we see how we got here. We have managed to position ourselves as almost equal partners in the development of the students and the pedagogy and the curriculum. So here's a quote from Nicholas Roy, who's a professor of aeronautics and astronautics and the director of the engineering part of MIT's Quest for Intelligence lab, that I solicited from him back in 2020. Nick has taught with us in a graduate level course that I'm going to discuss very soon. And he said that most scientists and engineers understand the need to disseminate results of research, but few have a solid grasp of why and how to have impact. Working with us, working with RAP, to teach students to use principles of rhetoric to frame research, articulate the technical gap, and explain why the research matters, has dramatically changed for the better not only how students talk about their work, but also how they think about it. And to get to that point, I want to take you through the whole trajectory of how we made it to essentially become embedded so much into the disciplinary thinking that now the kinds of things we talk to students about help them think about their work differently. So here's the argument. How can this alignment be possible? Well, we have to think about thinking about one's work or reasoning about one's work as having two equally important parts. One has to do with that first part that I showed you in the title, the ek didaskalias, which is training in intellectual virtues through teaching. So being exposed to core disciplinary rhetorical concepts, strategies, frameworks, or disciplinary thinking in action as you can annotate it in text or in oral communication by core concepts and moves. But also you have the ex ethos part, which is training in ethical virtue through habituation. So my argument here is that if we think of ethos as both an individual and a collective dimension, professional disciplinary ethos falls into that category. And also if habituation is the means by which individual ethos develops, in the same way then, professional ethos relies on ritual acts that form and manifest group identity. Therefore, we can have this kind of training by training a person in rhetorical action through appropriate rhetorical habits. And I'm going to show you how we did that in a couple of classes. So if you think about our history, the first thing to note is that we started back when Course 16, Astro, was thinking about putting capstone courses in their program. And that was 20 years ago almost. So these two courses, as you can see, went back to back, 16, 621, 16, 622, and they really had to do with designing a research program, a research and experimental program, and then being able to implement using software or some apparatus that you constructed, collecting data and reporting all the way back to a committee as a capstone on this data. At the same time, they recognized that, in order to do that, you had to demonstrate that you were able to use a communication strategy, implement it, and then orally and in writing, typically with your team partner, be able to explain your work to a team of extended team of stakeholders. In that effort, they brought in the writing program, they brought in RAP, and they said, let's help the students not only do their oral written reports, but also hopefully how to work together by having individual or team consultations. Now, this relationship started to build up, and very quickly it was becoming obvious that one of the learning objectives of the department itself had to do with effective communication. And soon, working backwards from the capstone course, new courses in communication with communication components were being developed. And a dedicated RAP lecture was embedded in Course 16 to be able to support students in their major throughout their academic career. If you take a look here on the right, you can see those experimental projects courses, but also flight vehicle engineering or advanced special subjects in aerospace systems or space systems developments. All of these are courses that the writing instructor, the RAP lecturer, worked with. So until that point, we have a single instructor following essentially the demands and constraints of the disciplinary curriculum as it's being developed by faculty in aerospace engineering, delivering some instruction and feedback to faculty and communicating with the students on a need basis, right? The faculty said we need the students to be able to do X for this course. The writing instructor was there to help support them. So the writing instructor started to develop a certain sense of ethos or credibility within that community by participating in the conversations that they were having about the curriculum, but always as a consultant, always having this position of someone from the outside coming in as a consultant. Now, in the spring of 2016, we were approached by Course 16, and they said, well, we have these third and fourth year doctoral students who are struggling with their quals oral presentation or the dissertation proposal defense. After their qualifying exams, after the written part, they had to do an oral defense of the work they were proposing to do. And that wasn't going very well. This was a high stakes presentation in front of a large committee of people who not always were able to see the value of the research or the gap. Core moves were missing. So the students had a very hard time with that presentation. So instead, they decided to develop a 3-credit, a 3-unit course and help students go through this process, but also by providing them with feedback. If you look at the subject description, what's important here is that this course is framed as emphasizing how to articulate a research problem, not just about communication skills, but the logic of how to frame and present the research. So it's not just, okay, let's polish up your skills, but how can we think of the logic of presenting your research? And how can we have the writing people, the rhetoric program, help you in that process? So in the beginning, we had in that version some lectures that we prepared to deliver, and that's what we were asked to do, to take students through some of the core concepts of rhetoric. So we talked to them about purpose, audience, context. We talked to them about some of the features of the rhetorical situation, exigency, some of the constraints of the situation, genre, quite a lot of conversation about audience. We even discussed with them some stasis theory, trying to understand what kinds of questions they had at hand and what kinds of arguments they would be able to make based on the questions that they had. In many cases, engineering deals with causation and possibly evaluation because you want to optimize things, right? You want to have a better aircraft wing. You want to have a better process on how to, I don't know, deliver things into space. But at the end of the day, there were some policy questions. What should we do that were pressing? So we wanted to give them a sense of a framework of how they can be thinking about their own questions. And also, we talked to them about moves, showing them some of the things we know from EAP, English for Academic Purposes, showing them what are the common moves that they would expect in this kind of quals presentation. To connect to what they have in their own field, we also talked to them about Hellmeyer's catechism. Hellmeyer was with NASA, and he had come up with this set of questions. If you look at them, you know, the moves, the rhetorical moves that we are all familiar with are right there embedded in those questions. And he was essentially saying these are the kinds of questions you should look into when somebody's submitting NASA proposal, right? And that was very useful because it had some credibility in the field. So we delivered these lectures. They were 3 very short lectures to kind of give them the overview of what the field is. We included some examples that we annotated from actual work that we had seen. And the course fared, we had mixed results for the course. The overall evaluation was a 4.6 out of 7. And some of the student comments at the end included things like, well, we didn't really see the connection between the lectures and the feedback, the comments we received. Some of the feedback and the comments were from technical instructors, and they didn't really use the same frameworks that we were using. Someone else said that, well, let's not think about the rhetorical aspect, but think about the scientific thinking process, because thinking leads to communication, not the other way around, which is, again, a very common misconception, or a very common way that engineers think about their own work. First comes the technical part, and then you communicate it. And the last one, it seemed that someone was concerned that the lectures that we had did not really speak to their audience, right? So they didn't really seem to understand what these concepts such as stasis or moves had to do with what makes a good talk. So there was some disconnect there. And then we started working very, very closely with faculty. And our goal was to shift to start integrating the idea of practical wisdom, the things that happen on the field, with, again, the concept of ethos that I described in the beginning. So we collaborated on the slide deck for the introduction of the concepts, and we had the Aerospace faculty deliver these first 2 lectures. And instead of a 3rd lecture, we had an example talk by the Aerospace faculty that also had some critique and feedback built into it. Finally, we added a component of lessons learned. After the first round of talks, we had one more lecture that identified patterns, and the students were able to go back and say, well, in the first round, we were able to see this kind of thing happening in framing, this kind of thing happening in the move to establish a gap, and so on. So we brought back these concepts, this time in larger patterns. And just to give you an idea of what this looked like, and these are slides that we collaborated on with the Aerospace faculty who were teaching in this course, they looked like this. Aristotle came in, but this time talking about rhetorical moves was put in very, very pragmatic terms. Don't talk about your research, don't do a chronological narrative, focus on a specific research question. Talk about your approach and your findings, and think about your audience. So it's essentially the same things that we were talking to them about without the Aristotle cover, but in very, very pragmatic terms, in almost assertions as these are the things you have to do. Also, we gave them the overall structure of a talk. What are the moves you have to make? Research question, frame the field, establish the state of the art, what's the technical gap, solution, results, impact of the results. These are very, very generic because we have many different kinds of projects in our answer, but this is a very generic move structure, but it seemed to work really well for the students. We even talked about stasis, but this time shifting it a little bit to have the technical gap precede the solution and move to the evaluation as the last step, because typically the policy questions, what should we do, are not really addressed in these technical talks. So we still kept the same framework, we still kept the same core concepts. At the same time, since we had examples from the previous year's talks, we were able to show them as examples of how to think through some of the core moves. For example, here's a problem statement. You have a design mission, what should be the next AD prototype, which leads to a vehicle architecture, and then this leads us to certain sensitivities when we want to optimize the vehicle architecture for different kinds of missions. All of that leads to a hypothesis which then gets explored in the rest of the talk. Similarly, we had students who identified the technical gap, and you can see here how the stasis comes into the picture. On the one hand, we have our desire to control emissions from gas turbines. On the other hand, we have a limited understanding of the mechanisms. So what do? How we resolve the problem? Well, we have to model the relationship between the two and then see how is that going to lead us to some solution. Since we made that shift, and since we essentially took the rhetorical concepts and integrated them within a more pragmatic, and we're going to talk about the idea of the practical wisdom approach, what happened with the student evaluations was quite remarkable. On average, they went up to 6.2 out of 7 in all those semesters. And here you can see, again, from one semester, what a typical feedback looked. My writing skills improved, 6.4 out of 7. Instruction and feedback was helpful, 6.6. The speaking task contributed to my learning, 6.6, and so on. So students clearly recognized the value not only of the technical feedback they were receiving, but primarily of the feedback they were receiving for their development of their communication skills. But this time, it was in a much more integrated manner. So here are some final thoughts. This type of integration and alignment that we all strive for as writing program administrators seems to be a product of both habituation and teaching. Especially if you think about rhetorical in structure and its alignment with disciplinary communication. This experience with course 16, and especially this particular course for 3rd and 4th year PhD students, demonstrated the value of integrating ethical education with practical wisdom. And in this case, again, ethical education is clearly connected to habituation, right? Finally, training the faculty in those rhetorical concepts and frameworks, and then giving them the opportunity to act as the rhetoricians, presenting them, has established a much stronger learning community of practice. Overall, it's been a very important model to see how we integrate communication into a disciplinary program which traditionally has been isolated, mostly because it's so widespread in all these different other subfields and disciplines that it didn't have a core. This was my presentation. If you have any questions and comments, my information is here below. I'd be happy to hear from you. Enjoy the rest of the conference.
And I will paste his email in the chat as well.
Hello, welcome to our presentation, Eliciting Students' Disciplinary Learning Incomes, Identifying Discipline-Specific Frameworks and Processes. I am Rebecca Thorndike-Breeze. My colleague Jessie Stickled-Sarah and I will present our work on a teaching team in a space system design capstone class in the Aerospace Engineering Department at MIT. This experience is interesting, not just because we brought our program's reasoning diagram approach to bear in the class, but because we deployed it in dialogue with students, often in the midst of our instruction. Throughout a dialogic process with students and technical faculty, we determined that the communication tasks and challenges of space system design closely aligned with the engineering tasks in the field. The image on this slide works well, in my view, as a representation of that alignment. This is an N-squared diagram, also known as a dependency structure matrix, or DSM for short. It is a key tool of systems engineering, and through our dialogic experience in this capstone, we've come to understand how it undergirds the aerospace community of practice. The matrix represents functional or physical interfaces between system elements, and by extension, between subsystems. Jesse will elaborate on this more in a few minutes, but for now, I will just say that we have found not only how essential the N-squared diagram is to aerospace in order to follow through on an integrated system design, but also that all the formal and informal communication genres, both explicitly defined and not, affect or are affected by the interfaces represented here. Thus, teaching students to understand how that disciplinary genre ecology propels or obstructs the key activities of the design team, and by extension, the design itself, has become a central goal for us as a result of the experiences we will now relate. This system design capstone class included a very real design project, a microsatellite or CubeSat with a scientific payload and a launch date in June of 2020. This date has, of course, since been pushed back due to the shutdown in March 2020 and subsequent issues that arose throughout the pandemic. Indeed, all of the work presented here occurred pre-pandemic. CubeSats are small spacecraft, around 4 inches on each side at their smallest, with an approximate volume of 1 quart. NASA established a CubeSat launch initiative called Educational Launch of Nanosatellites, or ELANA, to offer a, quote, low-cost pathway to conduct scientific and technology demonstrations in space, thus enabling students, teachers, and faculty to obtain hands-on flight hardware development experience, unquote. High school, university, and graduate students participate in ELANA programs, and you can find out more about that on nasa.gov. This kind of real-world project is a common feature of capstones in this department, unlike many other departments in which projects are more exploratory, less defined, and less closely tied to faculty research. CubeSats are a key focus of the lead engineering faculty's research, and this particular project was a continuation of work done by a previous team of undergraduate and graduate students as part of a summer institute in the department. Thus, nearly all of the students in this capstone found themselves in the middle of an ongoing project and needed to get themselves up to speed very quickly, much like they would in an internship or starting a new job. But in this case, almost everyone on the team was a new hire. Students were assigned to subsystem teams, which were coordinated by an integrative systems team and 2 undergraduate project leads, as well as the faculty and course TAs. Additionally, students had 90 minutes or more of lecture and 3 hours of lab every week to get them up to speed with their assigned subsystems. In this way, the capstone was a hybrid of a traditional lecture lab class and a situated learning environment. Very briefly, situated learning is the process of learning and development that occurs as novice students participate in a community of practice, and through regular opportunities to practice the activities and norms of that community, develop expertise there. Leib and Wegner refer to the unintentional nature of this learning as legitimate peripheral participation, where students move from the periphery of the community as novices toward the center of the community as they become more expert. Unintentional here indicates the emphasis of the activity. The objectives of the community of practice are the emphasized activities, not so much the education of novices. The structure of this capstone was such that, on the one hand, major emphasis was placed upon building upon the work of the previous design team in order to achieve a successful launch of the CubeSat in June of 2020. And on the other hand, to educate students, specifically to help students achieve the department's capstone goals of learning how to design an entire space system, including how to design a specific assigned subsystem and how to integrate that design with other subsystems. This hybrid of conventional lecture lab class and situated learning created a heavy workload for students, and often the links between the lecture or lab content and how to effectively design assigned subsystems for the term's specific project were not explicit or intuitive, nor were they intuitively obvious to students. As new communication instructors in the aerospace department, Jesse and I relied on our program's approach. As Michael Trice discussed, learning what our students already understand about communication in their discipline is essential to our program's approach to making implicit disciplinary reasoning patterns and core concepts explicit. As students advance from novices to more expert engineers, their identities are also shifting, integrating the priorities of their discipline. Overall, in our teaching, we seek to guide students to connect their existing knowledge, or what Wang Guerra calls their learning incomes, or what students bring with them when they come to school, to the new challenges they face as they learn to communicate in their disciplines. In this case, the case of this capstone, we at first assumed students had some experience with project-based aerospace classes, though not on the scale of the system design capstone. However, through conversations in office hours and at subsystem team conferences, we learned that, with the exception of capstone classes, students had very little exposure to project-based classes. Fortunately, many students had real-world experiences with team engineering projects, either through their work on MIT's extracurricular rocket team or through internships at such places as NASA's Jet Propulsion Laboratory, aka JPL, or SpaceX, etc. These conversations with students, especially early on, were invaluable to us as we designed class discussions and elicitation questions for our instructional time. So this slide presents a partial genre ecology of this space system design capstone, all of which we uncovered through our dialogic process with students and faculty. Time is short, so we're unable to fully discuss all of these, but my colleague Jessie Stickled-Sarah will go into more depth about our approach with specific reference to our work with system requirements, including the master minimum equipment list, also known as the MEL, N-squared charts, again, also known as dependency structure matrix, or DSM, and the major milestone of the class, the critical design review, or CDR. Jessie?
We weren't actually together, so we're switching videos.
Thanks, Rebecca. Lacking expert disciplinary knowledge, we used several methods to understand and teach these genres. Throughout the semester, we conducted many formal and informal interviews and discussions with the lead faculty, TAs, undergrad team leaders, and other experts in the field. These experts shared their tacit knowledge about the entire system, explicitly stating many logical connections that were left implicit in the texts themselves. It was clear that we would need to expose this reasoning to students before they could communicate effectively in the assigned and expected genres. So we analyzed the texts to which we had access to reveal relationships present in the genres, and we found ways to elicit what students did know to enable them to make reasoning and genres concrete and relevant. Early on, students were shown this figure representing the systems engineering process as it's understood in this field. Conceptually, this diagram represents the process of breaking a large project down into smaller manageable pieces and then reintegrating those pieces back into the whole system. Reading from top left down, the process begins with the design, starting at a high level and becoming more and more concrete down to the individual components. Then, moving back up the right arm of the V, we see the build phase from parts to subsystems to the full system. Now, students understood this conceptually, but they didn't understand how to do it. The key genres of this process are the design reviews, those acronyms marked on the V itself, which provide checkpoints and external evaluation and recommendations. Our class began where the previous class concluded, with the preliminary design review. Today, we'll look at 3 of the genres we used to teach students about integrating specialized subsystem knowledge into a whole collaborative system design. From the genre ecology Rebecca just showed you, you'll recognize the system requirements and the critical design review. And the N-squared chart, or SDM, connects the system and subsystem design. Now, when we initially requested examples of communication tasks in the class, we were given the previous semester's final design review. This was also the text given to students to catch them up on the previous semester's work. They were expected to spend the semester creating a similar document for the next review stage. Now, in this talk, we're going to look at some design review examples from a previous version of this capstone class, whose documentation is now public. And the purpose of that project was to observe an asteroid passing by Earth. As you might imagine, it was challenging to begin at this intermediate point. The document reflected, and to an expert revealed, the reasoning that connects high-level objectives to the specific component choices students were expected to make. Students reading design review materials understood their own subsystems, but didn't know who else they should be working with, whose designs would affect theirs, and what impact their choices would have on others. As a result, students operated with insufficient and out-of-date information, producing delays, inter-team conflicts, and late redesigns. And as non-experts, we didn't have answers for them. Instead, we relied on implicit student knowledge, expert knowledge from staff, and a chart like this one that Rebecca showed you a few minutes ago. This visual is designed to make explicit the relationships between subsystems. So the list of subsystems would appear on the X and Y axis, and those boxes in the middle would signal the intersections or dependencies. We learned about this genre in a conversation with graduate TAs, who suggested that both the chart as an artifact and the process of creating the chart would be valuable for student learning. We collaborated with TAs to define the concept, and during class time, we showed students where they could begin to learn about dependencies, asked them to enter their own team's information to a shared Google spreadsheet like this visual, and then invited them to practice by identifying the impact of a specific hardware change. Students reported having a clearer understanding of the position of their work within the whole system, and they said they were able to inform or request information from relevant subsystems more effectively than before the activity. Nevertheless, students still struggled to connect those cross-team dependencies to the genres they were required to produce and the reasoning that faculty expected. Let's look at one more example to see why this was so hard. Okay, the design review slides that students were given included information on the requirements for the mission, which looked like this. This is mission objective number 1. And students were expected to read long tables like this, which appeared at multiple points in the design review documents from the previous class, and infer both the technical reasoning and the rules of the genre. After reading these documents, students had to design their subsystems, select appropriate hardware, and explain why their choice was the right one. So, returning to the same design review we've considered before, here's a piece of hardware. This is Ralph. Where could students who had made this selection learn how to justify a particular hardware choice? How could they find the connection in prior documents? Well, all of the necessary hardware is maintained in the minimum equipment list, or MEL. And this is another implicitly defined microgenre. Reading left to right, this table shows several items in the instrumentation category, identifies their functionality, and states the requirements that each item satisfies. So Ralph is going to do some spectral imaging per PLD1, that's payload requirement 1. To find payload requirement 1, you'd have to go back to the subsystem requirements much earlier in the document. Okay, we know that those requirements come from system requirement 6, and that takes us back to the mission objective we saw before, M01, which states that the objective of the mission is to measure the physical properties of this particular asteroid. That's a lot. And this is just one fairly legible selection from the complex and implicitly defined genre ecology which students were expected to read, learn from, reason with, create, and use to persuade. Multiple different teams and roles would be involved in specifying and defining these relationships. To decode this piece of the genre, we combine textual analysis, here tracking terminology and hints at causal relationships such as requirement satisfied, with expert interviews. For faculty, the genres and microgenres like the design review and the requirements list provided everything needed to do this semester's work. But students couldn't effectively read and write in the expanded genres until they understood the reasoning patterns required in the discipline. For instance, the need to select hardware that would meet the defined requirements of the mission. Thus, we needed to decode the key genres of the field and the class, expose that reasoning to students, and then support students in deploying their own technical knowledge to successfully design their system and present it at the end of the semester. We've shown you just a few of the specific methods we used, but the most important insight for us was the same as it was for the students. We needed to integrate the system of technical knowledge with our own system of communication and teaching to provide our students with a coherent, cohesive education. Thanks so much for your time, and we look forward to your questions.
Okay. I feel weird thanking Jessie. She's the second part of my presentation, but thank you everyone for watching those videos. We had a question about feedback from Joanne earlier. If you scroll up in the chat, Michael and Jessie both answered that. So Joanne, you can chime in if you have follow-ups, but I also want to open the floor to any other questions just in the interest of time. Okay, so Michael and Jesse, would you like to share your responses that you just to kind of synthesize them for the audience?
Sure. So Joanna had asked how we reference or use the stasis in our feedback to students. And Michael had mentioned that in the class that Andreas described, which is 6995, it's an oral presentation class. And so we give live feedback to students essentially on their presentations. But in many other classes, the way that we give feedback on stasis is tied to the way that we've given instruction on it, essentially. So the thing that I just said here is that often we can tell students, you know, in your introduction, you're probably going to highlight value and you're going to highlight policy. You're going to make a recommendation to do a particular thing based on its qualities. For instance, it's got the right weight, or it's fast enough, or it's really efficient. And then so our feedback would be able to point out, you know, here you're talking about policy. I don't see the values. I don't see, for instance, the metrics that you're going to use appearing here. I'd like to see more of that. Maybe we would note that we see them somewhere else. So what we're doing both in feedback and instruction is helping students understand what it looks like to represent, for instance, definition or value, you know, in a computer systems design paper or in a critical design review. And then often observing, you know, where do we see it? Are they doing that? Why would it be helpful to do it in a particular location? Michael, did you want to add to that?
I think that covers it pretty well. I mean, there's a lot. Obviously, we adapt it significantly depending upon the classes, as Jesse is saying. But yeah, I think that the main thing to take away there is that we want to be able to have students be able to connect that to an example that they've observed and be able to pull apart what the stasis there are in those established sort of professional in the discourse examples, whether they be research papers or other presentations, and then be able to use those as keys or ciphers for explaining to students to what we're talking about when we're mentioning specific stasis, because it can be a difficult concept to wrap your mind around. So it has to be very grounded when you're providing that feedback.
So thank you for that. I really appreciate, you know, I'm really fascinated by this approach. I think it's really interesting. So in the future, and I know there's like, you know, confidentiality concerns with IRB, I would love to see much more of what it looks like in action, because what's going through my head is like, I love this approach. I have my own, you know, I have a different approach already that's more, you know, sort of genre based on MRAD to teach things. And so I'm just like, is the overhead of the stasis worth it? You know, adding that on. And so I would just love to see more examples of that so I can make my own sort of evaluation. So anything that you might, you know, have or could share about that, and especially about the amount of overhead, you know, the payoff for the amount of overhead in there.
Yeah, so one of the things that I would say about that, and we don't talk about it in this panel because we don't have one for Aero Astro yet, but this does connect. We did the workshop with the reasoning diagrams earlier in the week, and when we have a reasoning diagram for a discipline, which is basically just a way of mapping the high-level concepts and how they connect to one another for a discipline, we specifically label stasis as elements of the reasoning within those diagrams, and that is something that opens a lot of capacity for removing some of that overhead, because it's being integrated into the reasoning process. So we have that for a number of like 5 or 6 disciplines at this point in time, but we don't have one of those for Aero Astro currently. It's on the list.
I have to jump in and interrupt you now, Michael. We're a minute over our time, but that was really rich. Thank you for answering that question so well.